graphing a set of inequalities, right? Not equal signs, so less than equal to, the greater than or equal to. We're going to graph a set of them, so more than one equation. When we graph those all together at one time, it is called linear programming. When we have the goal of finding a maximum or minimum. So linear programming is what we are going to be doing. Now, in the past, you have graphed systems of equations before. That just means you've graphed 2 lines at a time or 2 inequalities at a time. When we graph those systems, you have a shaded region when you do inequalities, like we're going to do today. And the inequalities, the shaded regions are all of the solution sets. I knew where I wanted to get there, the words weren't coming out right. So the shaded region is all the solution sets kind of overlapping each other. You'll see that again when we look at the graphs in a minute here. Now the inequalities in linear programming, it's not just called a system of inequalities system. The inequalities have a special word because why not? It's English language, we might as well name it something else. They're called constraints. So that's C-O-N-S-T-R-A-I-N-T-S, not restraints, constraints. So a constraint is like a rule to follow. So when we get to the word problems, it'll be, okay, you have to manufacture all these products, you only have 100 hours to do so. So that's a constraint. It's a rule that you have to follow. You don't have an unlimited amount of time or an unlimited amount of supply or product. So we have constraints, those are the equations. The intersection, where the equations are going to overlap, is called the feasible region. F-E-A-S-I-B-L-E, region. What does feasible mean to you? Have you heard it before? Oh, that plan is feasible. What do you think that would mean? Doable. Yeah, the feasible region is like something that can be done. All right, so we're going to be overlapping, and it's a section of the graph that works out, the stuff that can be used. All right, so we have constraints in a feasible region. We'll see that in a minute. The feasible region is going to be our shaded region, our answers. Well, that answer is going to be in the shape of a convex polygon. That sounds fancier than it is. It means it's going to make a shape. It's going to make a square. It's going to make a trapezoid. It's going to make a triangle. Right? It's going to make a convex polygon. And we're going to be looking for a maximum or minimum value from this polygon. That's going to happen at a vertex. Okay? You remember the vertices? Those are the corners where the sides intersect of your shape. All right. Almost done with these definitions for things that you're not quite sure what they are yet. All right, so when we graph these, we're going to make a shape, we just said. And that shape is going to have sides on it. So it's going to be a triangle or trapezoid. We call that bounded when it has sides. So a bounded shape. So it'll be something like this, and we'll be coloring in like the triangle. There is something called unbounded, which means one side doesn't exist and it just goes on forever. We'll see that one time in a couple days here. But for today, we're going to have shapes with sides. All right, and finally, I have a new notation for you. Instead of just regular function notation, f of x, this one looks different. It is f of, we have x, comma, y. You say that it's f of x and y. Now, the reason we're going to use that is because when we are going to do our function notation today, we're going to have 2 variables, 2 things to substitute in, an x value and a y value. Okay? So we just learned a bunch of vocab that kind of doesn't necessarily make sense because we don't know what we're doing. So let's put it into some context here. This is what your quiz is going to be similar to later this week. You're going to be given a system of inequalities. A system means a set of more than one graph that you're going to make at once. See? Notice here, I have 3 inequalities here. Greater than or equal to, less than or equal to. And then I have this f of x and y function. You're going to ignore the f of x and y function for now. You're not going to graph it. We're going to end up graphing the first 3 equations, and this f of x and y guy is going to come back in a couple of minutes. So the nice thing about this example is that they're all solved for y. It makes them really easy to graph. So let's grab our pencil. We're going to graph the first. Ready? You got it. Okay. You should know how to graph this. We're going to start at 2. That's our y-intercept. And our slope is -1. Down 1, right 1. Now, the only thing is, sometimes we get a little lazy with our graphing. And this is one case where you have to plot as many points as possible and use a ruler. Because if you're not careful, you're not going to be able to find the vertices of your shaded region. So plot as many points as you can, and then use your ruler to carefully connect them. I know it seems tedious, but grabbing a line is not hard. But again, the corners of that shaded region are going to be really important. And if you're sloppy about graphing, you're not going to be able to find the corners. Now, typically, you have to shade for an inequality. This is y is greater than or equal to. So I want to save you guys a little bit of messiness on your paper. So I'm going to shade up here. You guys are going to shade at the end when I tell you to. Okay? Because you're going to end up having to erase a lot, so you might as well just wait. Let me do it for you. So let's think about this inequality really quick, though. Come on. There we go. If that says y is greater than or equal to, would you shade above this line or below this line? Above. All right, so I'll shade up here. You just pretend you shaded on your paper, and we'll do it later. Okay? All right, let's try the next one. This is y is less than or equal to 1/4 x plus 2. So now let's graph that line. We'll start at 2 again. It's okay that it's on the same point. And we go down 1, right 4. It is up. I did. I lied. I lied to you. Up 1 over 4. And now I'm... Alright, let's go back to a pen. Pen. Okay. My smartboard hates me. Hold on. Okay. There we go. Alright, and then use your ruler. Connect those really nicely. I'll use a different color here. Now if we're going to shade that one, it says y is less than or equal to. Where would you shade? Above that green line or below it? Below it, for less than or equal to. So, oh, I wanted green. Here we go. So we're going to shade down in that region. Now you should start to see a little sloppy part over there that has black and green shaded in this portion over here. So now we have one more graph. Y is greater than or equal to 3 over 2x minus 3. Plot it very carefully. We're going to start at our y-intercept at -3, and our slope is up 3 over 2. Now you should notice as you're graphing this one that some of the points are going to intersect. That is exactly what you want to have happen. We want the points to cross so that we get a really nice region. Alright, so let me graph the last one here. Line. Alright. Go down like this. Alright, so when I shade that region, I have y is greater than or equal to. Do I shade above or below? Above, that's right. So I'm going to go above the red here. And now that I've shaded all 3, do you see a spot on my graph where all 3 of those colors kind of overlap with each other? Where? Can you describe it? In the triangle. There's a triangle right here. That is called your feasible region. That's where all 3 overlap. That's what you color in. Right? You don't need the rest of this because that is not solutions to all 3 equations. We just want that little triangle. So again, the constraints are the equations. The feasible region is this triangle. Now you should be able to look at that triangle and say, oh, I have 3 vertices that are really nice ordered pairs. All those lines intersected. Now this is going to seem like a really silly thing to point out, but it's going to be important. How many lines did you graph? 3. How many sides does the triangle have? 3. When you graph 3 lines, your feasible region should have 3 sides to it, right? Which ours does. So I'm going to take each one of those ordered pairs, and it says in name the coordinates of the feasible region. So I'll start with this one. This ordered pair is 0, 2. So just write the ordered pair down for now. Your next one here is at 2, 0. And where's the last one at? 4, 3. All right. Now the reason we're only worried about the vertices of that triangle is because our goal is going to be to find, down here it says find the maximum and the minimum value. It doesn't really have a purpose today, but once we get to the application stuff, we always want to find a maximum profit or a minimum cost. All right, so the max or min is always going to happen at one of those corners. So we need to evaluate our function here. That's where this f of x and y equation comes into play. Now, x and y, I just wrote down 3 ordered pairs. What does each ordered pair have? An x and a y. Each one of these ordered pairs gives you an x and a y value. So that's actually, each ordered pair is the input for your function. So let's find f of, we'll start with 0, 2. 0, comma 2. That's your x and that's your y. You're going to put 0 into the x plus 3y for x and the 2 for y. Write down that notation though, because that'll help you later. We need to know where the max and min happened at. So we'll have 0 plus 3 times 2. What output does that give you? 6. Okay. Then we evaluate the next ordered pair. F of 2, 0. We're going to put 2 in for x this time, plus 3 times our y value, which gives us 2. And we'll do our third one, f of 4, 3. All right, so our x plus 3 times the y gives you an output of 13. So that's 6, 2, and 13. That's what we're trying to find here. So we're trying to find the maximum. What was the largest output that we got? 13. So you need to write all this down. You need to say that we had a maximum of 13. And what output, what ordered pair did that happen at? At 4, 3. So our maximum was 13, and that happened at the point 4, 3. Today, like I said, that doesn't really mean anything today, but it's going to have context starting tomorrow. Now, what was your minimum value here? We have a minimum of 2. At what ordered pair? 2, 0. Right, and that's the whole process. That's like the time-consuming part of linear programming. This is what your quiz is going to be on Friday. Not too horrible? Not too bad? Not bad? Okay, let's do one more together because that's not bad, slanted lines, but then when we flip over, we get to some lines that are not going to be slanted. So we need to remember which lines are slanted and not slanted, which is why we're going to do number 2. And we're going to do one more today. We'll do number 2. So I have 3 equations, and then I also, again, have f of x and y. It's not this time. We're not there yet. So we're going to start with the first equation. Y is greater than or equal to 2. Now, how many letters, how many variables are in this top equation? Just 1. So when I have just 1 letter, I'm not going to have a slanted or an oblique line. I'm going to have a vertical or a horizontal line. Do you remember what y equals is going to be? Is that going to be a horizontal or a vertical? A horizontal. How do you know it's going to be horizontal? What? Just because you know it? Well, if you don't know it, because there's probably at least 2 people in here that are like, I didn't know that was a horizontal line. What I tell my Algebra 1 students, and we did this recently in Algebra 1, was if I have 1 letter, and just 1 letter, and it's a Y, that means that that line is going to cut through the Y-axis. Your Y-axis is the vertical. So if you cut through the vertical, you make a horizontal line. So we're going to draw a horizontal line here at Y equals 2. Use your ruler so that you can darken it in. You need to be able to see that line because it's going to be part of our bounded feasible to shade at the end. You don't need to shade right now. So that one's okay. Then I have my next inequality, my next graph here. It's 1 is less than or equal to x is less than or equal to 5. Well, how in the world do I graph that? Good question. Yeah, it's not that hard, but it's not necessarily intuitive. I want you to break this one up into 2 inequalities. So if you cover up the right-hand side, we'll have 1 inequality, which is 1 is less than or equal to x. And then you're going to graph the other side. X is less than or equal to 5. What that tells me is that just visualize for me that I'm going to graph 2 lines here. I'm going to graph one line here at x is less than or equal to 1. Is that going to be vertical or horizontal? Vertical. So let's graph a vertical line at 1. Use purple here. All right, and then I'm going to graph another vertical line at 5. Yeah. Now, let me point out to you, it does seem a little silly, or not silly, but you might be wondering, well, why didn't I just write it like that? Well, this actual notation written as the compound inequality, you don't have to shade this in, but I'll show you, means that you would be shading in all the x's in between 1 and 5. That's why it's written that way. But in order to graph it so we can shade it, we have to graph 2 vertical lines. And I should have said this earlier, but I forgot. Why am I using solid lines for all of these inequalities? Yeah, they all have the equal to. Oh, that was not a pen. They all have the. I don't know. It doesn't work. And now it's back to the crayon. Oh my goodness. I give up. There we go. They all have the equal to sign underneath. Sign is a solid line. All of these are going to have solid lines. All right, I have one more equation. I have y minus 3 is less than or equal to x. Can I graph that one as it is? No. What do I have to get by itself? You have to solve for y. So we're going to add 3 to both sides here. And when I add 3 to both sides, I will get y is less than or equal to x plus 3. That's going to be the 4th line that we graph. Right, so let's do that one carefully. We'll start at 3. We have a positive slope of 1. You should, again, see that your graph is intersecting at really nice corners and ordered pairs here. And once you plot all of those points, you can connect them with your ruler. I'm going to ask the same question I asked on the last problem. How many lines did you graph? 4. So how many sides should our feasible region have? 4. Do you see a quadrilateral? Yeah, it's a trapezoid. It looks like this, right here. This is your feasible region. Shade it in. Now, if you wanted to, you could shade all 4 lines with the correct inequalities, but we have a bounded polygon here, so it's always going to turn out to be right in here. So darken in your vertices now. Make sure you know exactly where the vertices of that feasible region lie. And now we're going to write them down. Who can tell me one vertex here? Shout out, Bobby. 1, 2. Where's the next one? 1, 4. What else?
5, 8.
5, 8. And 5, 2. Right. Our maximum, that's right, and our minimum are going to have to hit one of those corners. Now, some people think just because this 5, 8 is the highest point that that's going to be the maximum, it doesn't always work out that like that. Sometimes one of the low points is the max. That's why you have to take each of those ordered pairs and put it into your function, f of x, y. So let's do that. Let's start with 1, 2. We'll take f of, and it froze again. It's tired. It did too much work today, I guess. F of 1, 2. So put the 1 in for x, the 2 in for y. You can do this on your own. You don't have to wait for me, but I'll talk through it here for the video. 3, 1 minus 2 times 2. you should get negative ones. It is okay to get negative answers for your options. All right, now we'll try 1, 4. Minus 3 times 1 minus 2 times 4. We should get an output of negative 5. Use your calculators if you need. All right, now 5/8. So f of 5/8. The 5 is your x, the 8 is your y. We'll have 3 times 5 minus 2 times 8. What does that give you? Negative 1. And last one, 5/2. Alright, so we have 3 times 5 minus 2 times 2. That's 15 minus 4, which is 11. Good so far? Are we okay with finding those? So now I just look at my outputs. Which one is the largest? Where's my maximum? Max of 11. What ordered pair does that happen at? 5/2. Right, so again, we will put that in context tomorrow, but for today, that's good. And what's your minimum value? Negative 5. Did you get negative 3? 3 minus 8. Oh, yeah. From negative 5, add the ordered pair, 1, 4. Alright, so this process isn't too bad, right? The hardest part for people is horizontal and vertical lines. So, here's what I have for you. You need to flip your paper over. We're going to skip the last one here. On the next page, you start a couple problems. Number 1 has some vertical, horizontal, has that compound inequality, so make sure you know vertical or horizontal. 2 also gives you all the steps. When you get to number 3, all I give you is the system. I don't give you any steps. So we'll see if you should be able to graph it, find the vertices, find the max and min without the help. The answers are all on there. Okay, so try those 3, check your work, make sure you're graphing first. This is what your quiz is going to be like on Friday. We'll do, here's